So, oh, what happened there? I was, okay, can you see my screen?
No, teach.
Let me try again, share screen. Can you see the screen now?
Seeing it now.
Good. All right, so today we're looking at understanding data analysis and common errors in research projects. So in this class, you are expected that you'll be able to make some simple statistical inferences. So in making those inferences, what you're doing is trying to make educated guesses based on a sample of a population. Did I forget to mute? Mute all, here we go, mute all, yes, great. Okay, so if we had the entire population and if the data we collect is accurate, then what we have is the truth. However, usually the truth is not always observable. Usually, in most research projects, what we do is get a sample, both in terms of the time and cost it would take to take the entire census of a population. It's not usually feasible. And if you even think about it, both in America and in Jamaica, where they do national censuses, usually every single person in the population is not willing to give the information. So even our national census doesn't include everybody. I know this for sure because I remember when I took place in the last census, the person who was trying to convince me, could I talk to other people in my neighborhood because very few people were agreeing to take the census. And I said, really? She says, yes. She said, maybe you can convince them because I can't. And by the way, she was getting paid per interview. So she was very interested in getting more, but I knew the value of it. And I realized that people just wasn't interested. But so the point is, even in the national census, is a subset. It's still only a sample because not everybody is willing. So based on that, you can take statistics to say, what can we know about a population from the sample that we have? So there are a number of statistics that can measure that different statistics. The only one we focus on in this class this semester was correlation, which tells how two variables are associated. And you can do that with two variables or multiple variables. So it basically correlations measure how one variable changes with another in terms of a linear relationship. As you know, the correlations vary from -1 to 1. 0 means that there's literally no association. 1 and -1 means that there are strong relationships. The sign of the correlation reflects the nature of it. If it's a positive correlation, it means that as one thing goes up, the other thing goes up. And if it's negative, as one thing goes up, the other thing goes down. So we have in the correlation, as I said before, you can see the strength of the relationship and you can tell if there's a linear relationship. And any correlations between a pair of values, right? If you actually want to look at the relationship between several variables and one variable, you need to do something like multiple regression, because you can do a whole series of correlations, but it's really not the same. If you really want to tell what is the degree to which a number of variables affect a 10th variable, the thing to do is a multiple regression, but let's not go there today. I don't even know why I went there in my talk. So in terms of variables, we can think about the more time you spend studying, the higher your test score will be. That's a direct positive correlation, right? The less money you put in the bank, the less interest you earn. That's also a positive correlation, because as one thing goes on, the other thing goes on. The more you exercise, the less you weigh. That as one thing goes on, the other thing goes down. So that's a negative correlation. And the less time you take to complete a test, the more you'll get wrong. I'm not sure this is true, because what I notice when I see students' results, I see that there's two things happening. Some people take less time are those who know nothing and they have a lot of wrong. And there are some people who take less time, who really know the material, who just take less time. So not sure this is right. So I'm gonna assume that if we were to take this data, this would be a low correlation. This might be true, but probably low. But if the less time you take to complete a correlation, the more you get wrong, that's also a negative correlation. And I'm saying that based on my experience, I think it's going to be not a very strong value, so the value will be like probably minus, somewhere between minus 0.3 and 0. It's my guess. That's my hypothesis based on experience. So we can use the strength of correlation to talk about the number, the coefficient, to talk about how to interpret what is happening with the two variables. So if the correlation coefficient is between 0.8 and 1, you have a very strong relationship. And that's true whether or not it is minus 0.8 to minus 0.1 or positive 0.8 to positive 1. And by the way, just as a note, there are 3 reasons why you should know this. 1, it's coming in the test. 2, this is in almost every research study, meaning even if you don't talk about correlation coefficients, this is just a basic thing. Like if you do statistical inferences, this is the most basic one to understand. And so as an educated person, you should understand. And thirdly, if you're going to pass this class, how could you not know this? So I think you really should review it and take this going forward. So if the correlation coefficient is only 0.4 to 7, we say that's a moderate correlation. If it's 0.2 to 4, it's weak. And if it's less than 0.2, there's a very weak or negligible or no relationship. So for example, if we take these two variables x and y, can anybody tell me, would you say that there's a correlation between these two variables based on the data on the graph? As in, is there a linear relationship? So if you go back to, No? So hold on. You couldn't remember this thing called the best fit line?
Yeah,
the best
there's
fit
a
line.
linear relationship.
The best fit line would come, and if you can see my mouse, about right here.
It's just that the correlation isn't 100%.
Yeah, the correlation is it's probably weak. I mean, we're not calculating it here. So if you go, so let me what's in the chat. Yeah, it's not if any. We can see a clear pattern. You can see the clear pattern. However, it's not a strong correlation.
Why I said no, miss, is because most of the values would fall below the line. So
what line? Here's the line.
like the line of best fit, miss. Yeah.
The line of best fit, you want to see if there are stuff before, above, and below. Not below. The line of best fit is not this way, The line of best fit is like this. It's going to kind of come here between, about here, like somewhere between, sorry. Somewhere between 1 and 2, and it's going to come up like this. That's the line of best fit.
Yes, miss. But just looking at it, miss, I was saying, most of the values, they would fall below the line of this. But Marashan can be, Marashan was wrong.
At any rate, let's move on. Sorry, 2 comments on that. One is, that is why, especially in something as a weak correlation, it probably is best to use a statistical tool to see what is the actual correlation. Because this is not one of the things I think that humans do really well. Humans do different things well and not necessarily looking at the graph and saying, but I can see there's a pattern. But we do have to ask here, is there a correlation here? Definitely. So I don't know if the graph is done perfectly, but they say here is a perfect linear relationship. That is depending on how perfect this line is. So is this positive or negative? Well, given that it tells you it's positive right here, but we know it's positive because a positive correlation is one that as one variable goes up, the other one goes up. See it right here on the graph. People just entering the meeting. Let me go up and let them in. Admit. All right. Right, so for this one, do we see a relationship between the variables? What is interesting, sorry, is it a positive or a negative relationship?
Would be negative.
Yeah, it's a negative or indirect or inverse. So they have here, they say it's a strong. It doesn't look strong to me. This is a graph for illustrations. It seems to me here, like it looks like a moderate relationship, but we're not calculating anything. We're just talking for educational purposes. So here's one where they actually calculated it. So here's the line of best fit, and this correlation is 0.892. And if you look at that, 0.892 is actually a strong correlation. Does that look strong to you? I think you can see a pattern that's clear. And this pattern is true no matter how you draw the lines. It just will look different. But it's really how close the correlation really, this number is really about how close the various data is around the line of best fit, and the line could be drawn differently depending on how you draw up the x and y axis. Now, if you look at this, is there a relationship between x and y? Okay, let's start. Is there a linear relationship? This is a yes/no question. As it can be?
No.
No, so there's no straight line that we can draw that is going to reflect the relationship. But is there a relationship? Oh, there's definitely a relationship. There's a perfect relationship that forms some kind of curve. So even though when you take this number, you find that the correlation is 0, there is a relationship. So Pearson's correlation, which is one we've been doing, where they use SPSS or PSPP, you're calculating Pearson's correlation, which looks for linear relationships. There are actually ways to calculate other kinds of relationships, but that's not what we're really focusing on. Right, so you can actually use other kinds of variables to look at the nonlinear relationships, but we're not focusing on that today. So we should also know that there's actually formulas to calculate the coefficients, but you can do that in software. So depending on the particular example we're using, let's say we got some data with weight and height, and we found that there's a lot of scatter. There could be a correlation of 0.541, which basically means that there is a moderate relationship.
Again, but this time
I thought I put, guys, if you're not asking me a question, can you kindly keep your mic muted? Do you have a question? Please and thanks. Right. So if the correlation between monthly rent and distance from campus for students, students are going to be willing to pay less as the location is further from campus. So it's not surprising that as the distance from campus goes up, the monthly rent goes down for students that they're willing to pay. So, you know, people like UTech, places that are very close there, they can charge relatively quite a bit of rent. And so that correlation is minus 0.903. And then I have one more example, exercise hours and study hours per week. Apparently there's no relationship between it in the data set that they brought, which doesn't surprise me. And the correlation was 0.109. But in addition to the actual number for correlation, we need to understand a couple of other things. So does a correlation mean causation? So if you remember back many weeks ago, we talked about different types of research studies. And I have read in my class, students writing that a particular, read about some research studies, and then they say that the research proves. Does anybody, so proof is the same as causation. Can anybody tell me what is the type of research that we use to establish causation or proof? Anybody in the class remember? I actually talked about this already.
Experimental research.
Exactly, experimental research. So with experimental research, the most common type is where you have something where we're controlling one or more variables. With natural experiments, you actually don't control anything. That's an exception. So with regular experiment, you control at least variable to see if another variable is or other variables are affected by it. So you would normally have an experimental group and a control group. If you're doing like maybe physics and chemistry, you don't even have a control. But if you're using human beings, you actually need to compare the experimental group with a control group, just in case you're actually not sure what's going to happen if you didn't have a control group. So for example, with medicine, you actually have to give people in a control group some kind of placebo, because just being given some kind of drug, people just get better just because. So you have to compare two groups in order to see what's the effect of anything you're doing, whether it's a vaccine, whether it's a pill, whether it's surgery, to see what's the difference. Right, so with that in mind, we know that experiments, we can deduce causes. And by the way, even one experiment, you still are unable to definitively talk about proof, because we're going to go through it shortly, remember that any one experiment is just a sample of what could happen. So you usually need many experiments before we talk about proof. So what we tend to do when we do one experiment, or any kind of study, we say things like the study indicates or the study suggests. We tend to not say anything about one study proves anything. But back to this now. So we can do studies, and the two most common studies that we do in computing would be surveys and experiments. So surveys include cross-sectional studies with questionnaires. Like, let's say I wanted to find out how you all felt about this class at this time. I could issue an online questionnaire and get the answers, right? But if I wanted to know if by being in this class you learned something, I would need to somehow ask at the beginning of class and ask again at the end, hopefully with some kind of test, something. But if I just ask you if you learned, that could be your impression that you learned, but not everybody's impression of their learning is correct. So sometimes when you just ask people their self-perception of something, it's not always accurate. So, but back to the story. We can do correlations of many things. So when you take a cross-sectional study, as in a study done all at once, and you take two variables and correlate them, what you see is if there's an association. You don't know, even if there's a strong correlation that is perfect, you still don't know if X causes Y or Y causes X. What you know is that there's a association. It could be that association is related to causes, but you don't know whether it's that way or not. So let me just take a second and come out of this and look at some spurious correlations. Okay, going and coming. So let's see, let's see, all right. For this yesterday. So let's look at this one. Okay, so just to show you some real examples. So look at this, US spending on science, space, and technology, as the number of suicides by hanging went up. So let's put it another way. As US spending on science went up between 1999 and 2009, the number of suicides also went up and down in the same way. Does anybody in here believe that US spending on science had anything to do with the people who are hanging themselves to death?
No, not each.
Right.
Not each.
Therefore, it's a spurious correlation. This one is even so ridiculous, not funny. Look at this one. Sorry, that one is like how many films Nicolas Cage appeared in, and it was associated with swimming pool drownings. This one is the consumption of margin per person, as per capita means, and the divorce rate in the state of Maine, USA. Look at this nice correlation. I don't think that how much people in the US were consuming margarine had anything to do with the divorce rate. This is the only one that to me seems semi-plausible, although maybe not. So the doctorate in computer science apparently is correlated to the revenue generated by arcade games. It also seems curious, but my joke is, I wonder if the people who are graduating were the ones writing the arcade games and then they were making more money. You know, I'm just thinking that's the only one to me that seems even semi-plausible, but it's what they. But you can see that this is real data, you know. So you can see that just because there's a correlation doesn't mean that it's due to a causal relationship. Everybody gets that? So let me go back. Current. Okay. So we also need to understand the significance of variables, and perhaps most people already understood this. So what you want to know is what is the probability that the estimate that you get from a statistic is produced by random chance, or is there actually really no relationship between the two variables that you're measuring by a statistic? So we've looked at correlation, but there are others. There is t-test, f-test, z-test, and many others that can be looked at, chi-square and the like. There are many kinds of statistical tests. All of them, we can say what is the statistical significance of that particular statistic in order to say, does that particular statistic have any meaning? What is really key is it likely to be correct? What's the probability that it's correct? So for every single discipline that uses quantitative research, there is a global accepted standard that we use something called a 95% confidence interval, or a significance level of 0.05. So it says here, we measure statistical significance by the probability that what we're observing is wrong. So if there's a 5% chance that something is wrong, it means that there's a 95% chance that it is right. Right? It's just 1 minus 0.05 gives you 95%. Right? And other common significance that is used is 0.01. So for people who want a more accurate level of confidence, they choose a significance level of 0.01. It means that when they finish a project, there'll only be a 1% chance that their results are wrong. And by the way, this is a 1% chance. So that's why people, if it's specifically important, tend to repeat research studies. So correlation coefficients tell us the strength of the relationship between variables, but they don't tell us whether there is causation, because it could be that it's spurious. Our coefficients are limited because they can't tell us if there is a marginal impact of X on Y. They can't tell us if there's causation, and if there's causation, what the direction would be. Because, for example, let's say X and Y are really causal. Is it that X cause Y or Y cause X? And correlations should never be used for forecasting the future. So, and if you wanted to do that, multiple regression would be a useful tool rather than correlation. But even multiple regression is not going to be useful unless you've done an experiment. So, for example, let's say we have some cross-sectional data about anxiety and depression, and there is a moderate correlation. Now, is it that anxiety causes depression? Is it that depression causes anxiety? Is it that people who suffered trauma as a child have anxiety and depression? Is it people who are in squalid conditions, you know? Is it that students who are attending UTech? The whole point is there's so many things that could be the cause of people having both anxiety and depression. It doesn't have to be that the two cause each other, right? So we don't know at all whether, if this is the case, that anxiety causes depression, whether depression causes anxiety, whether something else causes the two of them, or there's just a chance, a spurious correlation. You would need to do further investigation. And so if this is the case and you have like a doctor test for anxiety or see that somebody has anxiety, but they haven't done the test for depression, they should just give them an antidepressant until they investigate that they actually have an antidepressant, even though there's a good chance. What would be sensible is if they have anxiety to screen for depression, if they have depression to screen for anxiety, because there's a correlation once it's actually correct. So the thing about any particular correlation, there's going to be some amount of variability. So for in this particular one, there's a 49% variability in the patient's anxiety level with depression. So there's some potential possibility that these things have a relationship, but there's no evidence that one causes the other. All right, so at the end of it, what we really want to do when we're doing any research study is to figure out the true effect as much as possible. The 95% confidence level gives the true effect 95% of the time. So that means that if you did the experiment 100 times, only 95 times you get the real correct result. That's why when you do any study, even an experiment, you can only say this study suggests or this study indicates. Everybody understand why I'm saying this? Because you could have actually designed an excellent experiment, and even if you use 99% confidence level, there's a 1 in 100 chance that you did a study that unfortunately you didn't get the true result by definition. And nobody answering me, so I'm going to assume that you are following. So as I was saying earlier, by convention, p-values of less than 0.05, which means that we have a less than 5% chance that the results are inaccurate. Any p-value that is less than 0.05 are accepted as statistically significant in the scholarly literature. This is actually an arbitrary cutoff. It's now been that way for decades, and it could have been a different number, but that's the number that is now used. So there have been people write papers to say, but it's arbitrary. What if something is 0.06? But at this point, any study that doesn't meet this, we don't ever say it's statistically significant. You can still discuss it in your finding, but you will not be able to say it's statistically significant. I mean, if it's like, if you got a result that was 0.06, you could definitely say that, well, it was not found to be statistically significant. It'd be worth repeating the study to see if there really is a relationship between the variables, but it wasn't shown in this particular study. Yes? However, if you get a p-value of like 0.3 or 0.5, it's very unlikely to be any relationship between the variables, because the chance of it being inaccurate is very low. So as I was saying the same thing, when you have a p-value of 0.5, it means 5 out of 100 experiments will actually get an incorrect result, and that's called a type 1 error. And if p is less than 0.01, it means that 1 in 100 experiments, you get the wrong result. So we can use the confidence intervals to gauge statistical significance, which is just the same thing we've been saying all along. So 95% confidence means that p is less than or equal to 0.05. So you can actually, it's not required for our undergraduate projects, but often people who do statistical studies write out hypotheses. And when they write it out, they have both a null hypothesis and an alternative hypothesis. So if p is less than 0.05, we will reject the null hypothesis. Like, I don't know, what is a null hypothesis? So a null hypothesis could be if we create an animation tool to improve how students learn programming, the null hypothesis could be that this animation tool does not improve the academic performance of introductory programming students. That's the null hypothesis. The alternative hypothesis is that the animation tool improves the academic performance of introductory programming students. So if P is less than 0.05, we reject the null hypothesis, that there's no change. Instead, we essentially accept or do not reject the null hypothesis. In other words, if this is the case, there is an association. If this is the case, there is no association. So we want to look to, in order to interpret a correlation, we look at the numerical value of the correlation, the sign of the correlation, the statistical significance of the correlation, the effect size of the correlation. So we're going to move from that now to talking about common errors in research reports and presentations. And this is focused in a sense the learning process for major project, but it's actually also true for all projects. So in a research project, you're going to have at least one research question, and I've been asked by so many students again and again, you're allowed to have one research question once it is significant. Remember, a research question should be addressing a gap in the scholarly literature. So if you have two research questions, both of them should be in your conclusion. If not, you need to change your research question. There should be a match. There needs to be a clear organization with all 5 chapters. So, and they should be coherent, both inside the chapter and with each other. The chapter 1 is the introduction, chapter 2 is literature review, chapter 3 is the methods and procedures, chapter 4 is the analysis, chapter 5 is the conclusions and recommendations, and those should all be well organized according to basic principles. When you're doing that, you will have a supervisor who will help you give guidance and feedback. In your introductory chapter, what we've called the concept paper becomes an introductory chapter in a 5-chapter model. You should always have a problem statement, research question, purpose, and significance. I hope I know all of you know what those things are. So I'm just repeating this because we keep having people who come and they get all the way to the end and they don't have all of these things in their project. We don't understand why. So in a literature review, the introduction and the summary at the end doesn't have to have citations. However, each major section and each paragraph has citations. Why? Because it's a review of the literature. Moreover, in the literature review, you're expected not to talk about your proposed study. It's just literally a review of relevant literature. When you do that, at the end of the literature review, you're going to have a summary section, and in the summary section at the end, you are going to reiterate the gaps in the literature that you have already shown to people as you've written it out, right? And that would be directly related to the purpose of your study and your research questions, but you actually don't reiterate it right there. So the connection is, the literature review is connected to the aim of your study, but the aim of your study is not discussed in literature review, or it should not be. All right. Another problem with literature review is that it should be focused on the local, it should not only be focused on the local context. So a lot of students are doing a research study on Jamaica or the Caribbean. They don't want to write about the global context. I don't know why. You must look at literature related to the topic. However, sometimes they go too broad. So if you're looking at AI or machine learning for, I don't know, machine learning for, like I have a group right now looking at machine learning for advertising. You wouldn't in that project go about machine learning for all of business. That's just too broad. So you have to find a way to narrow your project on what you're looking at, because unless it is that there's almost no literature on that area, and then you have to broaden it in order to sort of talk about something that makes sense. Sometimes there might be a reason to use literature that is in another area that you're going to use for, often there's something called a theoretical framework, and we should spend a little time on that today, that is used, that you would put in your literature review, and that might come outside of the area that you're looking at because there's no theoretical framework in your area. That's the kind of time when you go outside of the specific area, if that's relevant. But usually you're not trying to give an overview of everything related to the topic. It's just focusing on the areas that's going to help you with doing the project. With methods, there are many things that are important. You must talk about the research design. So is it cross-sectional or longitudinal? Is it a survey, experiment, observation, you know, historical? What is the research design? You must talk about the sampling method. So what is the population size? What is the sample size? Are you using non-probability or probability sampling? And which of those in specific? So like I mentioned specifically, what's the difference between convenience and random sampling? Does anybody remember? Let's start with convenience sampling. What's that again?
Convenient sampling is when you just take anybody who you can get to do the research.
Exactly, and Gretchen says it as well based on availability. First come, first serve is convenient sampling. Random sampling, can anybody explain either conceptually or with the example?
Random sampling would be like when you have like a list of people who you would use for research, and you just like have like a list of names and you randomly take names from that list for your sample.
Right, so that random selection can either be literally a manual process if it's not too many people, or you use a computer to select randomly from the list. So notice you cannot, for all the probability techniques, including random sampling, you're unable to do it unless you have a list of the population. So either there's a pre-existing list, or you as researchers are going to go and find out that list. So if you want to do a research study on social media users, adolescents in Jamaica, and there exists no list, you either would need to get a list, which would be really hard, or use a non-probability sampling technique for the research project. So it's usually preferable to do a probability sampling technique, but depending on a number of constraints, including is there a list and what is the cost and time, non-probability sampling techniques are considered acceptable depending on the context. Oh, one more thing about method, you also would need to discuss the instruments and how you created the instrument. And it's always better to use instruments that are already been validated in the literature. Sometimes you actually make some modifications by testing it in your population. Sometimes based on the language, you might need to change the language because of the age group or the culture. But you need to discuss all those things. You need to discuss your ethics. So we have here, in terms of ethical considerations, you need to apply to a research ethics committee. So UTech, we have one. I was mentioning in Jamaica, we have 4 that I know of at least. There's a ministry, 5. There's at least 3 at 3 universities, at least. NCU, UTech, and UWI, maybe others, I don't know. And there's the Ministry of Health and Wellness, as well as the Ministry of Justice. At least those 5 I know about. So if you're doing research project, you're expected to apply for research ethics to say that like there's no potential harm to the participants, including the researchers. And when you're thinking about 3 principles. Does the research, is it going to be carried out with respect for persons? Beneficence means that it is expected to be beneficial in some way. And justice, if something goes wrong, we have a plan to essentially bring justice if people are harmed, or if the research goes right, the people in the study or the community where the study was done should benefit from that research. Right, so that's the summary of that. And with results, a lot of students, once they collect the data, they think, oh, almost finished the project. Well, actually, writing up the results is a non-trivial matter in the research. You should be using clear figures and tables, writing up the discussion in a fashion that's clear, and doing an analysis and interpretation of that data. You're expected to not only do a presentation that is descriptive statistics, you're also expected to do some analytical statistics like correlation, multiple regression, things like that, depending on your particular project. And then you would discuss the interpretation of the data, as in what does the data mean. And by the way, for those who don't get it, if you go back to what I was just talking about earlier for the first half of the class, I was basically talking at length about how to interpret correlations. So there are a few people in the class, maybe as much as a third, who that was just like, they already knew it. But I know from experience that a lot of you still don't quite get it. And you can feel free to go and watch videos. There are actually a lot of really clear videos about how to interpret statistical data that is online. All right, so you are expected in your discussion of your methods, in your analysis chapter 4, to talk about how results compare to the scholarly literature, right? You should have good graphs. And if it's a slideshow, the slideshow should also be clear. The conclusions obviously should follow logically from the data collected. I mean, this is like really painful to say the obvious, but having been doing both supervising and being a panelist for a very long time, it's actually amazing how students can actually show one thing and they get to the next section and they're like, wait, but this and this don't go together when you point out to them. They even like admit, yeah, so guys, you try to sort all that out before you actually get to the final presentation. You get your supervisor and other people to look at what you're doing. In case you're tired when you're doing it and you don't realize you're not being logical. Every single project has methodological limitations. So like a common one would be bias. It could be bias in the data that the participants provide. It could be bias in your interpretation. There are other kinds of limitations as well, but every research study has limitations, and so you should discuss it. One clue to do that is to look at similar kinds of research studies to see what are the methodological limitations. So for example, a quasi-experimental research by definition always has methodological limitations. Why? Because in a let me just say what a quasi-experimental research study is. It's a type of research study where the control group and the experimental group are not assigned by random chance. So for example, let's say we wanted to do this, as I was talking about earlier. We took some smart animation students along with some lecturers, created a nice tool to help students learn programming. And then the programming 1 and 2 class were to use it. So how do the students register for programming 1? It's not by random chance. It's basically, first come, first serve. The people who work tend to choose evening instances. So at the end of it, we actually don't have people in different tutorial groups that are identical, because it's not being assigned by a random process. And so when you compare, say, let's say there were 4 classes of programming 1, and you wanted to see 2 classes were given access to this animation tool and 2 were not, and we now compare the results of the academic performance. The thing is, if we even see at the end that students who had access to the animation tool did better than those who did not, there's a chance. In fact, let me just ask you guys, what is the chance that there could be a problem with that? Can anybody tell me why, based on that method, there could be a problem with that result? Nobody? But let's give you one example. So it could be that there is, it's very, we're out of last time. It could be that there is persons in the class. Let's say the people in the evening are more motivated and had more prior knowledge of programming. So, and they happen to be the ones who got the animation tools. Or even to say it was one evening, say it was 2-day class and 2 evening class. But what happened to be the people who got it are the ones who had previous programming knowledge, and we didn't limit for that. Let's make one simple one, the amount of previous programming knowledge. The previous programming knowledge would be a problem. So in addition to that, we obviously would need to like measure for that and do some kind of regression to see maybe but the point is, if you really wanted to figure out if the control group and the experimental group really led to a difference, it is best to assign each group randomly based on important variables. You can't do that in an educational environment where the class is already formed and you don't have control over that. So not going to go into that now. So every quasi-experimental research by definition has methodological limitations. This is written up in the literature. So you just go and find out what is the limitations of that kind of study, and you just put it, you just rewrite it in your own words. What is the methodological limitation? No study in the world, every study in the world has some kind of limitation. You need to write about it. And then your recommendations, which are 2 types. There are theoretical recommendations and there are practical recommendations. You need to talk about if what you recommend is your kind of expert opinion, but they must be plausible in your local context. So that's it.